Okay, hello everyone. My name is Charles. I'm just finishing my first year of Ph.D. at McGill University. I'm also affiliated with MILA, the Montreal, used to be the Montreal Institute for Learning Algorithms, but there's been some changes to the acronym, so it's just MILA now. So my work is mainly around healthcare and basically how can we use machine learning to improve diagnosis and decision making in healthcare. And so today I'll talk to you about one of the major themes of my research, which is trying to develop effective methods for diagnosing perinatal asphyxia from the cry of a baby. So what is perinatal asphyxia? It's when an infant is unable to establish regular respiration in the period after birth. And what usually happens is there is a shortage of oxygen supply to the vessels. This in turn causes inadequate oxygen supply to the brain. And there's slowly brain damage that happens, and depending on how long that happens without being checked, it could result to several disabilities, lifelong disabilities, or death of the infant. And so it's a pretty severe problem. I'm from Nigeria as well, and a few years ago I was living in Port Harcourt City in Nigeria, and a study that came out showed that the prevalence of asphyxia in that city was around 1 in 3 babies basically would be diagnosed with asphyxia at birth, or would have suffered asphyxia at birth. And this was pretty high because in Nigeria especially, the mortality rate from asphyxia is pretty high. It also turns out that it's a global issue, essentially. Every year, 1 million babies die from asphyxia. There is another 1-something million babies that suffer these lifelong disabilities that we talk about. And the WHO classifies asphyxia as one of the top 3 causes of newborn mortality today. So one question that could arise then in your mind is, what's the cause of this high casualty caused by asphyxia? Well, the first thing to keep in mind is it's a problem basically of the developing world. Most of the casualty occur in Africa, in South America, in Southeast Asia. And it's largely due to the shortage of access to early diagnosis. So the machine I showed there is a blood gas analyzer, and typically in Canada and the US, if your baby that's born would have their blood analyzed for oxygens, saturation, electrolytes, and all of these parameters that should be in place for it to be in good health. And if it's found that the baby is in short of any of these, it's immediately triaged to the intensive care unit to be taken care of by neonatologists. But this is hardly the case in Nigeria, for instance, where I'm from. And what happens is that nurses and midwives would depend on the visual signs to know that there's a problem. For instance, in the case of asphyxia, after a few hours, the baby is not breathing well, its limbs will go pale, and at that point, it's usually too late because the baby has suffered a long period of hypoxia and ultimately damage to the brain. And so this could go both ways, depending on the severity. Baby could die, or it could lead to disability. So that's it. And so I go to why babies cry was my next slide. But the reason we started looking at cry was the question is, could we find a way to develop a low-cost diagnostic tool for asphyxia? And that was what led me to that. And babies cry for many reasons, and this has been a decade-long study in the clinical world. There are the parents in the house will be familiar with some of these ones. The habitual cry where the baby just sits around and it's like, I've not cried and it's afternoon, and then it just starts letting it out. And or you are pushing your baby along. I don't have a baby, by the way, but I have many proxy babies from friends and family. And there's the other one where the baby is seeing another baby crying, and it's like, I feel your pain, I cry with you. And so there's that. But one of the things that clinical research has also shown is that the baby's cry is also altered by pathology, by things that affect its physiology. And this was really what we're trying to explore in this work we did. And so studies on this go back as far as the 70s. And in the particular case of asphyxia, there is this very strong connection between speech and breathing. First of all, the same region of the brain coordinates both activities. And in asphyxia, because newborns have not developed the ability to regulate or modulate the sound they produce, I can speak louder or softer if I want to speak. An infant doesn't have that ability. My accent has also been altered by where I was born, Nigeria. I speak like a Nigerian because the environment has influenced the way I articulate sounds. But the infant doesn't have any of these things, and so as one researcher put it, the infant cry is a true reflection of its inner physiologic state. And so when it's not breathing well, that directly causes an alteration in its cry patterns. And so this is like the theory and the things that researchers came up with back in the days, and the idea was, okay, so we have these tools, machine learning. Could we use this to learn these patterns that are caused, that are altered by the asphyxia and the infant cry? And if this was possible, then we could think of many possibilities of a cheaper diagnostic tool than the current standard in clinical care. This was the goal of the project, to apply machine learning to see if we could diagnose asphyxia from the cry of the baby. We've done some previous work on this, and the particular work I'm presenting here is based on a poster I showed yesterday at NeurIPS. And I'll bring it all together, the results we had before and the current thing that we just did. First of all, the data we worked with was, the first question too was, where do we get cries of babies that are normal and cries of babies that are clinically diagnosed to have asphyxia? So that's the only way we can reliably say, we've developed an algorithm that can diagnose this. And it was really hard because typically nobody's collecting this data and you'd have to do it in a clinical study. Fortunately, we found a team who had collected a database called the Shilanto Infant Cry Database. And their goal was a bit similar. We're collecting the cries of babies that had several pathologies in their neonatal intensive care unit. And we're able to get access to their data set, which was based on about 69 babies and had a bit above 1,300 cry samples. And so these were audio recordings of babies that were labeled as having asphyxia or being normal or having deafness or other conditions that they were recorded to have. And so the current work we did was using a transfer learning approach from adult speech. And this is a bit of a jump because in previous work we had developed support vector machines to solve this problem because it's a very small data set and jumping into a neural approach wasn't the best thing to do for sure. But then after that, and after seeing the limitations of that and asking the question of how can we scale this work, we asked the question of, we have thousands and thousands of databases, maybe not thousands, maybe tens, but at least databases that contain hundreds of thousands of samples of adult speech that we use for speech recognition and learning of text-to-speech and speech-to-text and things like that. Could we leverage this and learn representations that could be transferred to solve this task on newborns? It's true that adult speech is quite different from infant speech, but in the end, it's the same underlying physiologic process that results to speech being produced in both cases. And perhaps there's something that can be shared or something that can be transferred. And that was really the idea of this project and the work we did here. And so there's all sorts of databases for different tasks, and we chose 3 out of them to use for this problem. The VCTK database, which is about 109 English speakers, 44 case sentences, speakers in the wild, 2,000 sentences, and speech commands, about 65K recordings. So all of these are WAV files, basically, of people speaking and saying things. In some cases, they're reading newspapers and doing other things. The speech commands is basically people saying words like go, come, stop. And the idea is to develop machine learning systems to learn that, because that's exactly how the Amazon Echo and Google Home and those things work. You have to say, hello, Google, or hey. You have to make a command to make them wake up. So that was the goal of that database. And these were the 3 we focused on. And we tried to spread the source tasks, which is what we call them, across different kinds of tasks, just to see if there's a specific task that would help us do this better than another. Because when you are training a system to do word recognition, it's learning different things from the audio samples than when you're training it to, say, identify the speakers. In the case of identifying the speakers, you can imagine that what differentiates speakers is maybe the tone of their voice. Whereas in the case of defining words, what defines words is maybe the frequency patterns of those utterances. So this was the idea, and so next I'll just talk about the building block of our system, and eventually I'll piece it all together to show you what the system we built was and the results of that. So we extracted features, first of all, as male frequency cepstral coefficients. MFCCs have been the standard in speech recognition for a long time. Until today, people still do not train neural networks or things like that straight from the raw audio signals. Because in the audio case, it's just been more complicated to do that. And we still have to extract some kind of frequency representation of the signal before we can pass it to a neural network. I'll explain very briefly what the MFCC is, just to give people a sense of what it is. And essentially, every sound that we produce, the sound I'm producing right now, is spread across a frequency spectrum. And basically, if you look at one instant in time, you can check the amplitude of this sound across the spectrum of frequency. And this is pretty significant. Maybe to give a more close explanation, in music, when you consider one musical note, it's essentially one amplitude on the spectrum of frequency. And this is basically, and then when you look at maybe a chord, a collection of musical notes, that represents many amplitude points on the frequency spectrum. And really, that's what makes music sound nice, because you have it spread across the spectrum. And so the idea of the MFCC is really to extract the representation of a sound across the frequency spectrum to bring out more information from it. And so if you take a single time step, you can extract the amplitude of it across the spectrum like this. And when you have a complete audio signal, say a 1 second segment of signal could look like this. And if it was sampled at 8,000 hertz, then you would have 8,000 points here. And for each point, to calculate the MFCC, you basically extract the spectrum from each time point, from T1 to T2 up to the last time point. And the idea ultimately is to combine this into some kind of pictorial representation of the cry signal. So we've gone from that signal you saw here to this image you see over there. And the image basically, the x-axis represents time, and the y-axis represents the frequency. And so at each time point, we're extracting the values of the frequency, of the amplitude at each frequency point. And then the colors, they just represent the amplitude, so larger and smaller values. So basically, that is the MFCC representation that we take as input into our models and our algorithms. And again, this is more or less the standard in speech recognition literature. You would use some form of this as well. So in terms of methods, I had mentioned we had developed support vector machines to analyze this in previous work. Support vector machines are basically large margin classifiers that hopefully most persons here are already familiar with. For the neural networks we use a residual network. And the main feature of the ResNets is that they have this skip connection. So if the weight layers are basically whatever model you're doing, whether it's a fully connected neural network or a convolutional layer, that's what it's going to be. And the skip connection is really just takes the input and passes it over the layer into the output. And the idea is that it's a way of somewhat regularizing the model, such that if you have overparameterized this model, it could use that skip connection to learn the identity function and not have to overfit your data. So putting these things together, our system was basically a preprocessing step that extracts MFCCs from the input signal, feature extraction step that uses the ResNet to extract features from the signal, and ultimately a classification layer that is a fully connected layer to classify the signals into normal or asphyxia in our case. So we talked about doing transfer learning. So when we do transfer learning in our case, what we do is we train a network like this on the source task, whether it's speech commands database, and then we take the weights of the ResNet and we transfer that and use that as a starting point for training the network on the Shilanto database to classify birth asphyxia. So basically, we do two two models, one that we trained it all the way from scratch, and one in which we transferred the weights from the source tasks we've defined earlier into this one. So basically what I just explained now, yeah. So we have our 3 source tasks. We pre-train them to state-of-the-art performance. So the first thing is we want to train them to as well as it's done in the literature. So we try to reproduce the work that has been done in previous works to get them to as well as it is. Most got to accuracies of over 90% in training them. And then our target task is creating perinatal asphyxia. And using the database, we train 3 models, basically. Support vector machines, which is the classical approach. We call this one no transfer, which is we just train the model from scratch, initializing it using Glorot initialization. And I call this one SC transfer, the one that uses the speech commands. So essentially, all the transfer models perform better than the no transfer model. So going forward, I would only show the results of the speech commands transfer, because that was the best one, and then that was the one we analyzed in further detail. We evaluate using 2 metrics, especially sensitivity and specificity. Sensitivity measures how well are we doing in correctly identifying babies that have asphyxia, and specificity measures the accuracy, how well we are doing in classifying babies that do not have asphyxia, the normal ones. So you can see that's those 2 things. And then we do several analyses to just see how robust are these models. So first thing is performance. So here I show the performance based on specificity, sensitivity, specificity, and the average of both of them, which is something we call the unweighted average recall. And the thing worth noting here is, first of all models do pretty well on the normal patients. Because one, the data set is biased towards normal patients, but also they're a bit easier to identify the ones that are okay. And so they're all pretty fine and well with this. And you can see that this sensitivity, the one that measures the accuracy on the babies that have asphyxia, first of all, the one that is trained without any transfer learning does significantly worse than the others. Also, with the larger variance in its performance. The SVM shows that it's still a very good benchmark, because the goal in this study was basically, could we beat the SVM, which is the standard on this work? It still showed that we couldn't beat it by a big margin, because as you can see, it's a bit lower than the SC transfer, but the SC transfer has a slightly larger variance in its performance. But still, the SC transfer was a better model, in the end on this one. And we can see that using the UAR, which is the average of both metrics. So I just talked about that, so my arrow went to waste. So one of the other things we did was, could we see how robust these models are in both time domain and frequency domain? I talked about how we developed the MFCC representation. And the idea of time domain analysis was, what if we did not have the first 0.1 second of the signal that we used to diagnose asphyxia? We recorded the baby's cry, but the baby didn't cry in the first second, or something happened, the signal fell out. How would our model perform when we do that? And we repeat this for every 0.1 second segment, basically, of the signal. And this was the results of that. So basically, I showed the 3 models again, the SVM, no transfer, and the SC transfer. And one thing that quickly comes out is that the SVM's performance crashes much quicker than the neural models. The both models based on the ResNet are pretty stable with their performance up to, so basically what you're seeing here is that we use the full 1 second, we use only 0.9 seconds, only 0.8 seconds to classify, and going on. We don't retrain the model, we just take it into the trained model, just cropping out a chunk of the time segment. And you can see that, well, as expected, they all drop to the lowest possible UAR of 0.5. But the neural models are basically more robust to the time domain in this case, with the SC transfer roughly being the better one. So the second thing we looked at was robustness in the frequency domain. So what if it was not the recording itself that we lost? What if due to the recording device, due to some other issues, the sound was filtered and maybe some part of the frequency spectrum was taken out, either low pass filtered or band pass filtered or high pass filtered? what would happen? And in this case, what that looks like is taking out a chunk of, horizontal chunk now from the spectrogram. So what if we didn't have the frequency range from 0 to, say, 128 hertz? What would happen? And we do that as well for everything. And here's the result of that. And this one was pretty interesting for a couple of reasons. One, we see the same behavior again. The SVM is also the least robust to this kind of dropout in frequency ranges. So basically what I'm showing you here is the frequency ranges, 54 to 126, 126 to 205, and so on, just in case you don't see in a laterally inverted position. So basically, well, one, the SVM performs worse in just being robust to this dropout in frequency ranges. And the neural models perform really well. But you can see that there's all of this behavior happening in this region here. But that was really interesting because we also know that the fundamental frequency of infant crying is always below 500 hertz. And so essentially, one could say that all of the information we really need to diagnose asphyxia happens before 500 hertz, and we don't need any of the things that happens after it. And again, in this region where things drop out, the SVM, for the most part, performed worse, and the SC transfer was usually the better one in this region of dropout. So the last thing we looked at was, what if we added noise to these samples? Because in the real world, if we're using this in a healthcare center somewhere in Nigeria, what would happen is there's probably noise around the place, whether it's babies crying. So we had Gaussian noise here, the standard thing, children playing. We had sirens, we had dogs barking, and we added this to the samples too in increasing magnitude, and to see also how that affects them. This was a bit less decisive in its results, because we see that for the most part, too, the SVM does the worst, or drops fastest, essentially. But there's sometimes when it does, it acts like it's okay. But still, what we see consistently is that the model that uses transfer from the speech commands data set does pretty well across each of these. And there's one thing to just keep in mind between the speech commands data set and our data set, is that speech commands is learning to identify the signature of words. So each word you utter, whether it's go, come, stop, here, each one has a different time frequency signature. And perhaps what the results are telling us is that this is the closest thing to the kind of problem we're trying to model in predicting asphyxia, because that's exactly what asphyxia does. It alters the time frequency signature of the baby's cry. So this was basically the work we've done. So where is this headed? That's the next question. And this is headed we want to hopefully carry this, develop a machine learning model that will be able to be transferred into practice and used to actually diagnose infants. And so in our first proof of concept that we did with support vector machines, one of the things we did was integrate this into an app to see, how well would this work in reality compared to, whatever we did in Python. And we showed that we could achieve the same kind of performance using the mobile device as we did in our research. And some of the benefits of this over the current state of the art. So we've called it Ubenwa. Ubenwa means the cry of a baby in my language, in Nigeria, Igbo language. And the idea is that this would have many important benefits over the current way it's done in clinical practice. Because one, it takes a short time to diagnose. You don't have to sample the blood of the baby. It's non-invasive. It's cheaper. It's as expensive as a phone, which you can get for very low amounts these days. The other blood gas analyzer costs at least $10,000. And really, you don't need any expertise to operate it. So in these communities where there's resource shortage, you don't have experts, nurses, healthcare workers, midwives can actually use it to diagnose asphyxia. So what's happening also with the project? Well, we have a target now, because all we've done was with this database that's very small, collected by another team, that we've used to prove this concept. And we want to push the frontier and say, we need to get a more robust database, a more diverse database that cuts across geography and has sufficient sample to lead us to a point where we can develop something that we consider reliable and can start to deploy and test. And so we're working with physicians in Canada and in Nigeria, across institutions to do this, and that's the target, to acquire our own data, validate what we have, refine our models, and hopefully we can push them beyond the point they're at now, closer to 100%. Just want to acknowledge everyone who has been a part of this project over the last few years. And my research is supported by Vanier Scholarship in McGill. And thank you. Happy to take questions. Hi.
So, are you trying to use the app to collect the data? Like, they're trained the system?
Yeah. So the goal of our ongoing project now is twofold. One, to validate what we have now, just to ask the question of, okay, this thing we developed with this small data set, how does it even do on this new data we collect? But we also want to build a new database. So we're using the app to collect the data. Yeah. Yeah, Daniel?
Have you faced double infections that are confusable within the same vocal range?
Could you say that again?
Are there double infections that are within the same range, like pneumonia?
Okay, so basically, when we collect our data, the baby has to be clinically confirmed to have asphyxia, and there's a criteria for that. So they have to actually use the blood gas analyzer. So they check the saturation in the blood, they check the APGAR scores, they do neurological exams, because we want to be absolutely sure that we're collecting a very clean data set, so to say. But I mean, there'll probably be some, noise here and there, but we're doing our best to make sure that, and this is why we have to do this in the hospital, right? Because we want to collect clinically anesthetic data sets. Else we could go to YouTube and download, babies crying and use that as well. So hopefully we are avoiding the situations where there's multiple infections, and we have a whole inclusion criteria for our study. So the baby cannot have any congenital abnormalities, or it must be of a certain age, and so on and so forth. So because we're looking at only newborns within the first month of birth. So a newborn has to meet many criteria before it can qualify for the study as well. Yeah.
Is this criteria IRB approved?
Of course. Yeah.
So just to confirm, your data set that you used for your study used from 60 babies?
69, yeah.
1,300 participants. Did you take into account some differences between the data, since each baby has...
Yeah, so the question is around the splitting data sets into the training and test data, right? Is that it?
Because each baby has a lot of foreign sequences, so there might be some differences.
Exactly. So when we split our train and test sets, we made sure that we split them by subjects, by babies, not by samples, to make sure that one baby, all the samples is in the test set, and it doesn't split across both. Else we could enter a situation where we are actually predicting the baby instead of predicting the disease, essentially. I think one of the simplest reasons is that it's a very small data set. Neural networks need much more data to learn the features and then learn to classify them. And they are much more parameterized than SVMs. Yeah.
From what I understood, when you're adding the noise, you're just adding to the task set, and then you're using your trained model to evaluate them.
Yeah, that's right.
Have you also tried adding this noise to your training data so then you could augment your data and perhaps do it?
Yeah, exactly. That's a very natural next step. In this case, we want to just evaluate the model as is, but that's exactly what we should do. And we do that in image recognition, where you augment the data by flipping it, adding noise, and so on. So yes, definitely something that we would do in just developing our final model of subsequent research that we do, is to augment the data set using both the noise, using the time domain dropout, frequency domain dropout, and things like that. I believe those things will make it more robust.
And then also, have you tried any other ways of preprocessing
Yeah. Directed the convolutions is becoming the nice fad. Remember that it's mainly valuable. Like the benefit of directed convolutions is for like long-term dependencies. Like people have used it mainly to look at like that's what Google used for the work in which that caused all the hullabaloo, right? Yeah. So you want to be able to make coherent sentences over time. So in this case, it's really short audio segments we're looking at. So what we are doing is even if the baby has cried for 8 seconds, we break it down into 1 second segments and try to learn from all of them and average the results to get the best out of it. I don't know if there's any other, But you know, this is still like, there's going to be a lot of research that goes into this when we get our data. Now it's just a small database that we can only do so much with at the time. Yeah. Right.
So you can tell I'm more an engineer than a researcher, but iPhones have really flat frequency responses, and Android has this weird frequency response that's different from phone to phone. Do you know if that makes any difference in like which of the different audio models?
Yeah, well, one thing that we've seen consistently in medical research, in everything, whether it's imaging, studies that look at physiological signals, is that your recording equipment matters so much, because this one is developed by a different manufacturer, has different specs, and that alters things. So a very ideal situation for our study would be that we record the baby's cries with different devices. So each baby that is in the study, we record its cry with, different devices that are representative of their domain. Maybe one Android, one iPhone, one Samsung, one HTC, and things like that. But that would be too expensive. We don't have as much time with babies to do all of that. What we've actually done now is to just restrict that to only a Samsung phone, because Samsung has the largest share of devices in Africa, basically. So in theory, we'll be targeting, we'll basically be collecting our training set using the device that will be most seen in the real world in Nigeria. It's not the ideal situation, but that's what we're doing. One of the things we've done to also curb that is that we've developed the entire recording module ourselves in the device. So we're not using any of the recording softwares that come with the device itself, because those people add their own filters and things like that. So we specify our own things. If we want to filter the signal, we actually filter it. We have knobs for specifying the sampling rate, the encoding scheme, and things like that. So we try to manage the kind of preprocessing that happens to the signal. So the only thing we can't really alter is what's the microphone inside of it, that hardware. Yeah. Unless we make our own device, which is not an impossibility, but it's not being considered now. Okay, thank you very much.